So we're being walked through how to graph this function without using a graph calculator in Mobius. Okay, what they first want you to do is to identify a stretching factor. Stretching factor would be if there is, it's whatever the coefficient is of tangent. Okay, stretching factor of 2, a stretching factor of 1. That affects how fast the tangent function increases or decreases. So if you got a big stretching factor, it'll look pretty narrow. Keeps the same, that whatever number here doesn't affect the period. Okay, the original graph of tangent has a period of pi, and that's an important thing to know. Tangent has a base period of pi if you don't have b. Okay, sine and cosine had a period of 2 pi until you started changing that number b, the coefficient of x there. Tangent has a base period of pi. And tangent goes between negative pi over 2 and pi over 2 for that middle interval that's near the origin. And this is for tangent x. This is not for what we have up above. This is just the original graph tangent x. So the stretching factor makes this go up at a quicker rate. If you had a smaller stretching factor, like if you had something like 1/7 tangent x, that would give you a graph something more like this that flattens out a little bit more. Pretty rough graph, but the idea is that it doesn't have such a steep incline around that. Let's see, is that an inflection? Oh yeah, it doesn't have such a steep incline around that origin there. So that would be 1/7, and maybe this would be like 2 times tangent of x. And if you increase that to like 200 times tangent of x, then you've got something that's changing really rapidly. It's got a much steeper slope. Something maybe more like that. But you could play with these graphs in Desmos too, just to see what happens with the vertical stretching factor. That's a really rough background of what a stretching factor does for us. So the stretching factor is what we might have thought was the amplitude back in terms of sine, cosine. So there's only a 1, and that's a coefficient of tangent x there. Okay. If that was a 2 or a 4, that would be our stretching factor 4. The period, okay, so the period for tangent and cotangent is a little bit different. It's pretty close, but it's a little bit different than sine, cosine. It's pi, not 2 pi, divided by the absolute value of b. But in our case, b is 1, so the period for this is pi. Oh. Now, if this is a 2x minus pi over 6, then the period would be pi over 2, right? This number here would be the coefficient. Since there's no number written in front of the x, it's just 1 for b. And don't forget, b is not the period. You have to use the formula for whatever trig function you're using for the period. If it's sine cosine, it's 2 pi divided by absolute value of b. If it's tangent or cotangent, it's pi divided by absolute value of b. Okay, and so we're supposed to enter all the asymptotes on the interval of this period, negative pi to pi, right? Because p is the period. I think they define that right there. So we're supposed to find all the asymptotes. Now this is tangent of x, right? Tangent of x minus pi over 6, I should say. Tangent is the same thing as sine, so I'm just going to rewrite this as sine x minus pi over 6 divided by cosine x minus pi over 6. And vertical asymptotes happen when a divide by 0 error is possible. So since we get cosine x minus pi over 6 in the bottom, what we really want to know for vertical asymptotes is when the denominator equals 0. So we got to solve that equation. Okay. There's actually an infinite amount of solutions to this equation, because if you try to use your calculator, use arc cosine is what you'd usually want to do, which sometimes looks like this in the calculator, or I might say ARC cosine. Either one. Your calculator, you're going to want to keep in mind, is just going to give you one answer, but it's a trig function and it repeats itself, so it's going to have an infinite amount of answers, so you'll want to interpret that answer if you do use a calculator. Oh, I forgot to do inverse cosine on both sides. Okay, it's an inverse, so it's undoing cosine. And so the whole point of using that red cosine It looks like it's to the negative first, but that's actually inverse cosine. The whole point of doing inverse cosine is because we're trying to get x by itself. That gets rid of this cosine here because an inverse of an original function leaves you with just what's on the inside, because it was the identity function when we looked at it before. Now this, if you need to evaluate this without a calculator, remember trig functions usually take in an angle, they spit out a side ratio. An inverse function means you switch the roles of x and y. So now instead of taking in an angle and giving us a side, now this is saying, hey, your ratio is 0. What's the angle that corresponds with it? For cosine to be 0, for the cosine ratio to be 0, cosine is the x coordinates. Cosine is the x coordinates on the unit circle. So this is where cosine would be 0 because this is 0, 1. Right? The x coordinate at this point is 0. So this would be a place where cosine is 0. So if you punch this in a calculator, you might get a decimal equivalent of pi over 2. I think that's probably the typical one they give out. But look, there's an infinite amount because you could also have 3 pi over 2, or 5 pi over 2, or 7 pi over 2. You can keep rotating around that circle. So we'll handle that in just a second. We've almost solved. Now we've figured out what this is without a calculator. You can add pi over 6 to both sides. So real quick, some mental arithmetic. This is 3 pi over 6. 3 pi over 6 plus pi over 6 makes 4 pi over 6, which is 2 pi over 3. Just double checking my math there. 3 over 6 plus 1 over 6 makes 4 over 6, which is 2 over 3. Yep. Okay, so that's one vertical asymptote. Remember, we're supposed to find all of them on this interval. So here's pi, so a little bit before, at 2 pi over 3, we're going to have a vertical asymptote because that would cause a divide by 0 error. Now to find the other ones, we're only looking on this interval from negative pi to pi, it said. So what we could do is we could say, hey, this thing repeats itself every pi units. So let's back this up 1 pi, right? Because it has a period of pi. And if you subtract that by pi, you get another one. You get x is negative pi over 3. And then you can try backing it up again. But if you do, you're going to get a vertical asymptote of negative 4 pi over 3. That's outside the interval that Mobius has asked for. Okay? So we only found 2 asymptotes in that interval. We found x equals 2 pi over 3 and x equals negative pi over 3. And again, you could verify that with Desmos, but like on the test, like we said before, you got to show everything without relying on technology, telling us what's happening with the algebra or the trigonometry in the background. And now this last part asks us to select the correct graph. What I'd want to first look when I pick a graph is I'd want to look for those vertical asymptotes. So if this is pi, then I'm going to draw in red a vertical asymptote that I expect to see. Okay, I expect it to get infinitely close but never touch that red line. And then same thing about negative pi. I expect it to get infinitely close but never touch negative pi over 3. And I think that is probably enough to spot the right graph, because you should see that classic tangent function after that. Oh, actually, tangent should go the other way, right? I just checked that. So 2 pi over 6. Sorry, second guess myself there for a bit. Yeah, tangent does go in this direction like I originally thought. And what I was doing to check myself was I was plugging in a value. I said, okay, well, let me plug in negative pi over 6, see what that spits out. And when I did, that gave me a negative value on the y-axis, which means it's got to go in this way. If I plugged in negative pi over 6 and I got a positive value, then I know the graph's supposed to look like this. So I'm going to look for asymptotes at negative pi over 3. This should be 2 pi over 3 because that was our other vertical asymptote. And then I'm looking for that the tangent function going in the correct direction, rising as we read it from left to right.